This lecture is going to be on beam deflection and matching boundary conditions. So this will look at an extended version of the beam deflection equation formulation and how we get to the final version of being able to find our constants of integration. So the first thing is a little bit of review from the beam deflection review. Overall, we have our deflection curvature relation, which is our moment is equal to our constant modulus of elasticity times our moment of inertia. And in some cases that will be a constant, in some cases it will be varying. Our EI is the bending stiffness of the beam, while M is the internal bending moment. Rho is our radius of curvature, which is the denominator in our deflection curvature relation. Another component is our 1 over our radius of curvature is about equal to our V double prime equation. V is our deflection curve equation, and V prime is about equal to theta, where theta is the slope. So when we do our integration, V double prime is related to our 1 over radius of curvature, V is the deflection curve, and V prime is our slope. Our bending stiffness is multiplied by our 1 over rho relationship to equal our moment, and if EI is constant, then the equation can be integrated and lead us to our slope and deflection equations. The second part, these are the two examples we did when we were looking at the initial part of beam deflection. So it was a constant distributed load as well as a cantilever beam with a point load at the end. This led us to a view of our deflection maximum, looking at the boundary conditions relative to the particular setup for the beams. So there's a couple steps listed for the procedure for determining the slope and deflection of statically determinate beams using integration. These are the same steps that we use to evaluate the beam deflection relationship in our initial setup. These are just written out to be a little bit more stepwise descriptive in terms of overall what we do in terms of the rigidity with our beam deflection. Double prime is equal to M, and then leading to the integration, which gives us our slope and deflection equations. Additionally, the boundary and continuity conditions tables are available in the textbook, but these give a good reference point while working on some problems to give what our boundary conditions for the second and fourth order equations would be relative to particular beam setups. Again, most of the ones that we'll do will be related to second order equations, but the fourth order relationships are also provided. So if we look at a couple of evaluations in terms of matching boundary conditions, then there may be more than one moment equation to find in order to evaluate the overall beam. So in the ones we looked at previously, we only need to evaluate one moment equation relative to the beam setup, and that was either the cantilever beam with a point load at the end or the uniform distributed beam. Alternatively, we may have situations where we have more than one moment equation, and one of those situations is shown on the left, where we have a relationship where there's one equation that relates to the increasing version of our moment and another equation that relates to the decreasing version of our moment, seen in M1 and M2 on the left side, shared moment diagrams, as well as the right side diagrams, which will show essentially loaded beam. So if we look at matching boundary conditions, the moment diagram showed that lines up with M1 and M2 were different. One was increasing, one was decreasing. And in that case, we cannot have one equation that describes both lines, M1 and M2. And so in that case, we'll need to break the beam into two different regions, 1 and 2, identified in the red 1 and 2 on the right side of this beam description. So if we break this into two descriptions, or two regions, then one will be 0 is less than or equal to x, which is less than or equal to L over 2. And the second will be L over 2 is less than or equal to x, which is less than or equal to L. And these two boundary conditions are formulated by looking at the individual regions relative to the coordinate system along x, where our beam separates. So if we look at the first side, which is the left side, this is the 0 to x to L over 2 section. So we can cut this beam and look at the free body diagram to get the relationship for the moment equation. So we'll have our initial setup where we have our point load at the end. That is represented by P divided by 2. So this is our overall free body diagram. And if we cut our beam on the left side, then we have our L over 2 relationship for the distribution in the x direction. So our free body diagram, and we'll look at the left side of our cut. Then we can evaluate the moment equation relative to this cut version of our beam. So I'll put a 0 here to signify our relationship. So since this is our positive relationship, we have down and our positive moment. And then our P over 2 for the left side of our beam. So in this, we'd have our left side of our beam, which is going to be distance x, relative to that cut point 0. So the first thing is we have the distance of our x to the cut. The shear force and bending moment are in the positive direction, and we want to use 1 as the subscript to show our region, which is shown on the V and M. So we can do our summation of moments about point O, which gives us our summation of moments about point O, M1 minus P over 2 times x is equal to 0. So this gives us M1 is equal to P over 2 times x. So we can do the same for the other section, which is L over 2 to x to L. So we can have our original, and then we can now cut our beam on this right side. And then we can have our free body diagram where we can cut to the left, or look to the left, or look to the right. And in this case, we'll look right because there are fewer terms to deal with, and also we can include that right side P over 2 load. So since we're cutting and looking to the left, then our bending and shear values will look in that direction. So we have our point 0 again, but in this case, we're looking at the distance being L minus x, because now this is the right side of the beam, so section 2, and so we're looking at the entire length of the beam minus the section that we're individually looking at. So we have L minus x, because left end, because it's from the left end of the beam. So we can do our summation of moments about this side. So we have summation of moments about 0. So we have negative M2 plus P over 2, and then L minus x as the distance. So in this case, we have M2 is equal to P over 2, L minus x, which would equal P over 2 times L minus Px over 2. So since the moment equation is discontinuous, then set up as if there are two different deflection equations. So now we can look at our left section again. So this is region 1. So we have EI V double prime is equal to M1, which is equal to P over 2 times X. We have EI V prime, which is P over 2 X squared over 2 plus C1. And this leads us to our deflection equation, which is EIV P over 2 X cubed over 6 plus C1X plus C2, which gives us our constants of integration. Additionally, we have our right side, that's L over 2 to X to L. So this is region 2. So we can get our equations as EIV double prime is equal to M2, which is P over 2 L minus X, which is equal to P over 2 times L minus PX over 2, which leads us to our slope equation, which is EIV prime, P over 2 L times X minus PX squared 2 times 2, plus a new constant of integration. And then we get our deflection equation, which is EIV P over 2 L X squared over 2 minus PX cubed 2 times 6 plus C3X plus another constant of integration, which we can say is C4. So now we need to figure out the constants of integration, and we need a boundary condition for each constant of integration. So in this case, we want to look at the original beam, which involves a simply supported situation. And at x is equal to 0, we don't have any deflection. So at x is equal to 0, we don't have any deflection, so V1 is equal to 0. At x is equal to L, we also don't have any deflection, so V2 is equal to 0. So one support lies in region 1, while the other lies in region 2. Since we have 4 constants of integration, we need 4 boundary conditions. And this is known as matching boundary conditions. If we look at the boundary between region 1 and region 2, there are a few things that we need to do in order to preserve that continuity of the beam to give us the relationship that we see that splits this from region 1 to region 2. At x is equal to L over 2, the deflection from region 1 has to equal region 2. So x is equal to L over 2 is equal to V1 is equal to V2. If not, then the beam would not have a continuous displacement in the vertical direction, and it's like the beam would be broken. In addition to the deflection condition, there's also a condition on the slope, and the slope evaluated from this particular spot or the boundary spot have to be the same. So we have x is equal to L over 2, V1 prime is equal to V2 prime. Additionally, since the EI, which is our rigidity, has been carried along the length of the beam as well, then these can also be written as matching boundary conditions. So this is EIV is equal to EIV2, and EIV prime is equal to EIV2 prime. So if we look at our overall boundary conditions relative to those situations, the continuity of the beam as well as the individual endpoints of the beam, then what we can have is for 0, x, L over 2, then we have x is equal to 0, V1 is equal to 0, that's E, I, V is equal to P over 2, x cubed over 6 plus C1, x plus C2, so C2 would equal to 0, and for L over 2 is less than or equal to x, which is less than or equal to L, we would have EIV2 is equal to P over 2 L x squared over 2 minus px cubed 2 times 6 plus C3x plus C4. So that would give us 0 is equal to P over 2, L cubed over 2 minus PL cubed over 12, plus C3L plus C4. And I forgot to write this part, so this is x is equal to L, V2 is equal to 0. So this has 2 unknowns. And we can look at, we want to go to the slope equation and set EIV1 prime is equal to EIV2 prime, where they are both evaluated at L over 2. So for 0 is less than or x is less than or equal to L over 2, EIV1 prime is equal to, this is it, x is equal to L over 2. This is P over 2, L over 2 squared over 2 plus C1. And for L over 2 less than or equal to x less than or equal to L, you have EI V2 prime is equal to P over 2 L over 2 minus P L over 2 squared over 4 plus C3. So we can set these two equal to each other, and we can get our deflection equation, which is EIV1 P over 2 L over 2 to the third over 6 plus C1 L over 2 plus C2. And C2 is 0. So now we can get EIV2, which is equal to P over 2 L over 2 squared minus P L over 2 cubed over 12 plus C3 L over 2 plus C4. So if we set these equal to each other, then our equations for our input looks like this. And if we set these equal to each other, now we have 4 equations and we know C2. So we have 3 equations and 3 unknowns. And we can evaluate this by solving C1, C3, and C4. Overall, the algebra can be kind of tedious. And if we have this relationship, you could stop with the equations relative to this point. In the homework problems, it's a good idea to go ahead and evaluate these, but the equations could be set up as far as our main evaluation. If you have a matching boundary condition problem on a test, you can stop at the setup of the equations by applying the support boundary conditions and the matching boundary conditions, but for the homework, you can go ahead and solve these.